Hi guys, welcome to your last lesson on Chapter 7. Lesson 7.6 is on solving exponential and logarithmic equations. As it sounds for the vocab here, the vocabulary says that an exponential equation is an equation in which the variable expressions occur as the exponent. So for example, b to the x is equal to y. Something involving variables as the exponents, those are exponential equations. Now logarithmic equations would be log base b of y is equal to x because b to the x is equal to y. And so a logarithmic equation would have your variables being in a logarithm, whereas your exponential equations are going to have your variables as part of an exponential function. Basically, there's really no reason that you would have to know the difference between an exponential equation and a logarithmic, except for basically just recognizing the fact that these two kind of go hand in hand, because the inverse of an exponential function is a logarithmic function, and so you'll be taking inverses a lot. Just like the opposite of add is to subtract and the opposite of times is to divide, the opposite of squaring something is to take the square root, and the opposite of using an exponent is taking a logarithm. So we'll be using those ideas as inverses as we start solving some of these functions. All right? All right, some property of equality for exponential functions. This is about the cheesiest thing in the world. Basically what we're saying is says if b is the base, is a positive number that's other than 1. So again, if the base is not equal to 1, b to the x is equal to b to the y if and only if x is equal to y. And all we're saying here is if we have the same base in both cases, then these exponents have got to match. So for example, 5 to the x equals 5 to the 4th, well then x has got to be equal to 5 because 5 to the 4th power is going to be the same as 5 to the 4th power. All right? And then if x is equal to 4, then obviously 5 to the x is equal to 5 to the 4th. So that's that if and only if business here. We don't really have to show it both ways, but we can use it both ways. And so I guess that's kind of the point here. All right? So let's take a look at an example here. We've got 64 to the x power and 16 to the x plus 1 power. Now we have to use properties of exponents to simplify these, because in order to use our property that we just learned, our property of equality for exponential functions, the big key is that the bases have to be the same. And in our case, 64 and 16, well, they don't match. So we've got to rewrite these powers so that they do match, at least they have the same base. So I'm going to pull the x power off of 64, and I want to think to myself, what base could I use that's somehow going to make a 64 and a 16? Well, that base would have to be 4, because 4 to the 4th power, 4 to the 3rd power rather, is equal to 64, and 4 to the 2nd power is equal to 16. So the base I really want to use here is 4. So I want to write 64 as 4 to the 3rd power. On the other side of this, I'm going to pull the exponent off of 16, set it off to the side, and rewrite 16 as 4 squared. All right? Now, the power of a power property, okay, the power of a power property says whenever you have two things, a power being raised to a power, and I know it doesn't really look like it's being raised to because the x is below the 3 here, but this becomes 4 to the 3x power because we multiply our exponents. This one's going to be a little shakier, but this is going to be 4 to the 2x plus 2 because we're really kind of doing this, right? It's the distributive property. And so this becomes 4 to the 2x plus 2. Now, because these have the exact same base, we know that if these two have the same base being raised to a power and they're equal to each other, then 3x has got to be equal to 2x plus 2. All right? A little bit of algebra tells us if I take away 2x from both sides, I get x is equal to 2, and so my solution is 2. Always, always important in this lesson and in many lessons to check your answer. Make sure that your answer makes sense. So 64 to the 2nd power is supposed to be equal to 16 to the 2 plus 1 power. Well, 16 to the 2 plus 1 is 16 to the 3rd, and 64 squared on the other side, 64 squared happens to be 4,096. And on the other side, 16 to the 3rd power is also 4,096. And since they're equal to each other, we know that my solution is a good one. All right? Let's try another example here involving our logarithms, our exponential functions. In this case, we just want to take the log of each side, all right? Now, we can certainly do it this way, and there's a couple different ways we might be able to look at this question. And we'll get to taking log in just a few minutes here. Let's take the log first. So we can take the log, and it doesn't matter here. We're going to take the log base 6 because the base is 6. So we want to take the log base 6 of each side. So this becomes log base 6 of 6 to the x power is equal to log base 6 of 27. All right? Now, what we get to do then is we get to say then, look, because we're taking the log base 6 of 6 to the x, all right, log base 6 of 6, essentially this all kind of goes away and we end up with just an x because it's base 6 and the base is 6, so then this becomes x. All right? So x is equal to log base 6 of 27. All right? Now, log base 6 of 27, we're going to have to use our change of base, right? So this is log base 6 of 27. So this, when using our change of base formula, this becomes log base 10 of 27 over log base 10 of 6, or common log of 27 over common log of 6. By the way, you could also do natural log of 27 over natural log of 6. Totally fine if you wanted to use a different base. In our case, since we use the common log, we're using a log base 10, but you can use the natural log if you want to. In any case, you're going to get the same thing. We end up getting something about 1.84. All right, the solution is about 1.84, and if you did 6 to the 1.84 power, we're going to get something pretty close to 27, so that's good enough. All right, now the other way I was alluding to this too is we could rewrite this in logarithmic form. This is log base 6, and again, this would be 6 to what power is equal to 27. 6 to the x power equals 27. Rewriting this as a logarithm by definition of a log, and we can kind of avoid some of this business by taking the log of both sides. So again, just another way to do it, and now we just jump right back in where we were. But that's the exact same thing. Okay? All right. Our next example then, we're going to kind of take a little bit of a look at something involving a natural log now. In this case, we want to solve for this thing. In order to solve for this thing, we've got to get this term all by itself. All right? And to get this term all by itself, we're going to have to get rid of the 6 and the 8. So if this just said 6x plus 8 equals 20, you would be pretty good at this. You could take away 8 and divide by 6. Nothing different here. We're going to subtract 8 from both sides. 20 take away 8 is 12. Divide both sides by 6. You get e to the 0.25x is equal to, and if I divide both sides by 6, I get 2. All right? So then I have e to the 0.25x is equal to 2. Since my base is e, I want to take the natural log of each side. Okay, by taking the natural log of each side, basically natural log base e of e, this all goes away, very similar to before. This becomes 0.25x is equal to the natural log of 2. All right? From there, okay, if we want to solve for x, we're just going to divide both sides by 0.25. All right? I didn't plug this in ahead of time, so I don't know what the natural log of 2 is, but if you take the natural log of 2 and then divide that result by 0.25, you get something in the neighborhood of 2.77. So again, when you plug that back into the original, we're not going to take the time to do that, but if you do 6 times e to the 0.25 times 2.77, and then add 8 to the whole thing, you should get something very close to 20. And again, very close because we had to round that number off. All right? Again, kind of a segue when we get into this part right here. Instead of taking the natural log of both sides, this was e to the 0.25x power is equal to 2. All right? And so if I wanted to change that to logarithmic or to logarithmic notation, this would be the natural log base e of 2 is equal to 0.25x because e to the, again, this is an e to the 0.25x is equal to 2. So if I wanted to go from exponential notation to logarithmic, you know, again, that's really going to be the exact same thing, except we don't have to write the e there because it's natural log. Okay? So you can kind of throw that in there as well. All right. let's take a look at the checkpoint problems. You guys try these 4. There's quite a bit here. Make sure you're trying these 4 checkpoint problems, and we'll be right back with solutions. All right, the first example, this is 3 to the 7x minus 3, and then 9 doesn't match the base, but I know that I can pull the 2x power off of that, and I can rewrite 9 as 3 squared. Now, power over power tells me that this is the same thing as 3 to the 4x power. Now, since they have the same base, we get to set their exponents equal to each other. I get 7x minus 3 is equal to 4x. All right. Take away 7x from both sides, you get negative 3 is equal to negative 3x. Divide by negative 3, and you get x is equal to 1. All right. Okay. In our next example, you know, the text is going to tell you to take the log base 5 of both sides. All right, and so log base 5 of 5 to the x basically all just becomes an x. All right, and so x is equal to log base 5 of 72, which if you want to use your change of base, we can use the natural log of 72 over the natural log of 5, or we can use the common log base 10 of 72 over log base 10 of 5. In either case, when you work all this out, you end up getting 2.657. So what we're saying is 5 to the 2.6 power is going to be equal to 72. All right. Now number 3 is kind of a messy little bugger. So let's just kind of get this part alone. Okay. So the first thing we're going to do is we're going to add 6 to both sides. So this becomes 8 to the 3x plus 2 power is equal to 11. All right. Now changing this back to logarithmic form, my base is 8, my exponent is 3x plus 2, so this becomes log base 8 of 11 is equal to 3x plus 2 because 8 to the 3x plus 2 power is equal to 11. All right? Now, this is log base 8 of 11, and to evaluate that, we're going to have to use our change of base formula. So we're going to have to do log base 10 of 11 over log base 10 of 8. And then from that, we're going to subtract 2. So this is log of 11 over log of 8. And then from that, we're going to take away 2. And then once I've subtracted the 2, then we'll divide the whole thing by 3. And so I'm just going to kind of put that all over 3, because this is essentially what I need to plug into my calculator. All right? So we're going to fly over to our graphing calculator here. All right, so here's our graphing calculator. Here's our mess of work that we have here. So it's log base 10 of 11 over log base 10 of 8. That's part's over here. We've already typed that into the graphing calculator. And so we'll go ahead and we'll execute that. And then from that, we need to subtract 2. Okay, so again, I apologize for I have to turn the pen off to click over on the calculator. From there, I'm going to subtract 2. And I get negative 0.84, blah, blah, blah. And then I have to divide that result by 3. And I get negative 0.2822, all right, which is really quite a mess, all right? So going back over here, for all of this, I end up with x equals negative 0.2822, blah, 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 all right? Now, because we got such a messy number here, not a bad idea to check, and so we'll go back to the original. This is 8 raised to the parenthesis 3 times second answer, that brings back my previous answer, and then plus 2 and parenthesis. And now when I get that number, I'm going to subtract 6, and I should get 5, and I did. Okay, so that is the correct answer for that one. Again, that one's pretty messy. And then finally for the last one here, this one is not nearly as bad. For this one, we're going to take away 2 from both sides because we want to isolate the exponential part of this. Divide both sides by 3. And you get e to the 0.5x power is equal to 1, because 3 divided by 3 is 1. Now, we can save ourselves a ton of time with this, guys, because what do we can raise anything to what power and get 1? Well, if you answered that 0, then you're exactly right. So e to the 0 power would be equal to 1. The only value of x that would make this exponent equal to 0 is x equals 0. And so like I said, we can save some time if you recognize that. If not, at this point, we would take the natural log of e to the 0.5x equals the natural log of 1. All right, and so this essentially cancels out. I get 0.5x equals the natural log of 1. natural log of 1 is 0, and so 0.5x is equal to 0. Divide both sides by 0.5, you get x equals 0. Okay, so a couple of methods of solution on that one. Hopefully one of them suits you well. And let's go ahead and fly over to the next page here. On the back side of this, we now talk a little bit about properties of equality for logarithmic equations. So we spent the first half of the lesson talking about exponentials. Now let's talk about logarithmic. Okay? It says if b, x, and y are positive numbers where b is not equal to 1, then log base b of x is equal to log base b of y if and only if, and once again, as you guessed it, x is equal to y. As long as the bases match, these things have to be the exact same. So log base 3 of x is equal to log base 3 of 8. Then x's have to be equal to 8. If x is equal to 8, then log base 3 of x is equal to log base 3 of 8. And once again, they show it both ways. Because of the biconditional if and only if, we'll be using one of the two methods. Okay? So don't be intimidated by our first example here. Many of you guys are probably looking at this and saying, what's the answer? But in this case, because they're both log base 7 of the exact same thing, and these are both log base 7 and they have to be equal, so that tells me that 6x minus 16 has to be equal to x minus 1. Okay? The logarithmic property of equality says that if they're the same base, then these things have to be equal to each other. So what we're going to do then is we are going to subtract 1x from each side. So we'll take away the x here, and so I get 5x minus 16 is equal to negative 1. Add 16 to both sides. And so I get 5x is equal to 15. Okay, divide both sides by 3, and I get x is equal to 5. Okay, so my solution is 5. You know what, it helps to be able to divide, guys. 15 divided by 5, or I'm sorry, 15 divided by 5. We're going to divide both sides by 5 because the leading coefficient here is a 5. Dividing both sides by 5, we get x is equal to 3. All right, so my solution is 3. So hopefully you're using pencil, not pen. And now to check my solution, I'm going to plug that in. This becomes log base 7 of 6 times 3 minus 16. Log base 7 of 3 minus 1. This becomes 18 minus 16, which is 2, so log base 7 of 2. And over here is 3 minus 1 is 2, and so log base 7 of 2. I don't actually care what those values are, but because they evaluate to the same logarithm, I can stop and move on. Okay? All right. Now, the next piece of this talks about this idea of exponentiating to solve. You can use this idea. I'm going to show it to you, and then I'm going to use a little bit different way, what I think is significantly more clear. In any case, this says, because this is log base 5 of 3x minus 8 equals 2, I've got this kind of a messy thing here. What I want to do is I want to exponentiate each side using 5 as a base. So this ends up being my exponent, and this ends up being my exponent. Because this is 5 to the log base 5, this effectively cancels out, and this becomes just 3x minus 8. 5 to the second power is 25. From there, we're going to add 8 to both sides, and I get 3x is equal to 33, and dividing both sides by 3 tells me that x is equal to 11. Okay? The solution is 11. Plug it in to check. This is log base 5 of 3 times 11, which is 33, take away 8. On the other side, this is, this is log base 5 of, and then 33 minus 8 becomes log base 5 of 25. And because 5 squared is equal to 25, log base 5 of 25 is equal to 2. All right? Now, I'm going to save, instead of this exponentiation idea, because to me I think that's a little bit confusing, we're going to take the form of this log base 5 of 3x minus 8 is equal to 2, and I want to write this in exponential form and solve it as an exponential problem instead. If my base is 5, this becomes 5 squared equals 3x minus 8. Because again, 5 to the second power equals this. That's the definition of a log. 5 squared is 25 is equal to 3x minus 8, and I'm right back in the mix with things right there. So you can do that either way. Again, I kind of like rewriting it as an exponent instead of thinking about this exponentiating stuff. So when we get to exponentiate in this problem right here, I'm going to do things a little bit differently. So I'm going to kind of skip a few steps and get down into here, okay? All right, but let's get at it. First thing that we have to remember is from the previous lesson, when we do this, we have to recognize this is log base 10 of 5x plus log base 10 of x minus 1. Since it's the same base and we're adding, that ends up being the product of those two things. And so this is log base 10 of 5x times x minus 1 is equal to 2. Now, it says exponentiate each side. Because this is log base 10, we're going to do 10, blah, blah, blah. You know what? I don't like that. I'm going to say this is log base 10, so this is 10 to the second power. And I'll rewrite it over here. 10 to the second power is equal to, 10 to the second is equal to this mess, which is 5x times x minus 1. All right? Well, what is 10 squared? Well, that's 100. And then on the other side, we're going to do 5x times x. We're going to use our distributive property. 5x times x is 5x squared minus 5x. All right. Now, this is a second degree polynomial. Unfortunately, we're left in a situation where we can't factor this. Because we've got things on both sides. I don't want to use the quadratic formula here, and because of the x, I can't solve with square roots. So I have to subtract the 100 from both sides to get it over here. And I get 5x squared minus 5x plus 100, minus 100 is equal to 0. All right. Now they tell you in the book here to divide each side by 5. I want to think about it as factoring a 5 out of everything. So this becomes 5 times x squared minus x, and then minus 20. But then since the zero product property tells me that 5 can't be equal to 0, I'm going to ignore that one as a potential solution. And so now I'm left to factor. I want two numbers that multiply to negative 20 that add to negative 1. Well, two numbers that multiply to negative 20 that add to 1 is 4 and 5. To get negative 20, I need 4 and negative 5. And so the factored version of this is x minus 5 and x plus 4. And so the product of those two things is equal to 0. So my zeros are then x equals 5 or x equals negative 4. All right? Now, we've got two solutions to check here. Hopefully you've got a chance to write all this down. If you don't, pause your video and finish writing, and then we'll pick up on checking in just a second here, okay? All right, so we're right down here in our check. We have our two solutions, 5 and negative 4. Please keep in mind that taking the log of a negative number, this number right here has got to be positive. Because again, this is 10 to some power over here. It's got to be a positive number. Since this is positive 10, it doesn't matter what the power is. All right, it's going to be a positive number. And so if this was the log of anything negative, it's undefined. Well, let's plug this in and check. Okay, this is log base 10 of 5, because again, our x is equal to 5. And so back from the beginning, this is log base 10 of 5 times 5, log of 5 minus 1, because again, this was my x and this was my x. Okay, 5 times 5 is 25, and 5 minus 1 is 4. And since this is plus, that becomes times. We end up 25 times 4, which is 100. Log base 10 of 100 is 10, because 10 to the second power is 100. Okay, and so long base, this becomes 10 squared, which is 2. Okay, so in any case, this one works out. All right, so 5 is a solution. Let's try the negative 4. This is 5 times negative 4 plus negative 4 minus 1, which is negative 5. And right here, this becomes negative 20. And as soon as you see this is negative and this is 20, because logs of negative numbers is undefined, this negative 4 is not a solution. So we talked about this in the beginning of the lesson. Make sure you're checking your solutions to see if they are extraneous. All right? Now, I need you to try the 4 checkpoint problems at the bottom. All right? Part of what you guys are going to turn in tomorrow is going to be to check your checkpoint problems to see if you've attempted these. So not only do I want the answers, which I'll give you here in a second, but I also want you to have shown the work. So try these for me, and we'll be right back with a solution. All right, since we're taking the natural log of each side of this, because it's the natural log using the same base, basically I get to say 7x minus 13 is equal to 2x plus 17. This is an Algebra 1 problem. I'm hopeful that you guys can solve this one by now. So that's gone and that's gone. I get 5x is equal to 30, and divide both sides by 5, you get x equals 6. I will tell you if you plug that 6 back in there that it does work, so you don't have to take the time to check that solution. How about for number 6? In number 6, like I said before, they say exponentiate each side with a base of 3, and that basically gets all of this to go away. I get 2x plus 9 is equal to 27. What I say is rewrite this in the standard form, rewrite it as an exponential. The base is 3 to the third power is equal to this, which is 2x plus 9. But it doesn't matter how you get there, you're going to get there, right? All right, so minus 9 from both sides, we end up getting 2x is equal to 18. Divide both sides by 2, and x is equal to 9. Next one's a little trickier. Because this is log base 4, I'm going to use my exponential idea and say this is 4 to the 5th power is equal to 10x plus 624. Now, 4 to the 5th power ends up being 1,024 is equal to 10x plus 624. And when I minus 624 from both sides, I get 10x is equal to 400. And when I divide both sides by 10, I get x equals 40. And once again, when you plug that one in, it will work. Okay? Now, I'm going to wipe this off. I'm going to start over again because I'm going to need a little bit more work for number 8, a little bit more space here. All right, so this is log base 6 of x minus 9 plus log base 6 of x is equal to 2. Because this is the sum of these, this becomes log base 6 of x minus 9 times x is equal to 2. All right, because it's the sum of these two and they have the same base, we take the product of x and x minus 9. Now, once again, your base is 6 here. So I'm going to use my definition of exponents, my definition of logarithms, to say this is 6 to the 2nd power equals this mess. So this is 6 squared is equal to x minus 9 times x. When I distribute the x, I get 6 squared, which is 36, is equal to x squared minus 9x. Now, because I can't solve this second degree polynomial simply by taking the square root, I have to minus 36 from both sides and set it equal to 0. So I get 0 equals x squared minus 9x minus 36. Okay? So then we go back to our old grid and we find two numbers that multiply to negative 36 that add to negative 9. Two numbers that multiply to 36 that add to 9 happens to be 3 and 12, because 3 times 12 gives me 36. And the negative 12 is going to give me the negative 9 that I want. All right? And so my two factors of this guy end up being x plus 3 and x minus 12. All right? So because the product of those two things is equal to 0, that means that my zeros are at x equals negative 3 or x equals 12. These are my two possible solutions. Now, if I plug negative 3 in for x right here, this becomes log base 6 of negative 3, which, as you know, is undefined. And so this solution is out. And I will tell you, if we plug the 12 in, it does work, because you do 12 minus 9, which is 3. So it becomes log base 6 of 3, and then log base 6 of 12. And you guys can do the rest of the check on that. But the other solution does, in fact, work. All right, so that concludes our final section from chapter 7. Again, this can get really tedious if you don't know these properties of powers, especially things like this. When you add two logs with the same base, we end up taking the product. So some properties you want to brush up on before you get started on that assignment.